In this video we're going to be having a look at sequential logic circuits. Now a sequential logic circuit is a circuit which has an output that is both a function of its present input or inputs, I should say outputs as well, and the previous condition of its inputs and or outputs. And it's this part that says that we've got a function of its previous condition, which means that sequential logic circuits have memory. So drawn as block, right, a combinational logic circuit on top with some memory, some outputs, or it could even be some inputs added back in, so there's our combinational circuit, and there's our memory. And we may have sometimes a clock signal added into this. It doesn't have to be for a sequential logic circuit. Alright, so the entire box now represents a sequential logic circuit rather than just the combinational circuit. Now when I'm talking about memory, we're not talking about RAM or flash memory or any of the other types of memory that you might associate with computers. We're actually just talking about a logic circuit like a latch or a flip-flop. So there are two main types of sequential logic circuits. There is the latch and the flip-flop. Now, the latch is typically with set and reset inputs. It will hold its value until an input changes, and importantly is normally level sensitive. And we'll go over what that means shortly. Versus a flip-flop is a latch, so all of this with a clock input and the output changes, so it holds it and then its output changes when a clock edge is detected. And so this one is what we know as edge sensitive. Alright, so level sensitive, if I had inputs looking like this, I'm interested to see whether it's 0 or 1. Alright, so I'm interested in the darker bits here. What is the level of the input signal? Versus edge sensitive, I'm either interested in, is it a rising edge or is it a falling edge? So logic 1, logic 0, rising, or also known as a positive edge, and falling edge. Now in some texts you might find slightly different definitions for our latch and flip-flop, but that's the one I want you to remember for the purposes of this course. Right, so level sensitive is interested in whether it's logic 0 or logic 1, edge sensitive only on these edges. Right, that's only the time that we're interested in their operation. So let's have a look first at latches. Now a latch can be constructed from AND gates, or it could be constructed from NOR gates, as I'm going to do here. And the NOR gate one's slightly easier because our inputs are what's known as active high. We're looking for high levels rather than low levels. And let me make sure I get my connections correct here. What we get is some feedback. So the output of one OR gate goes to the input of the corresponding other NOR gate's input, and vice versa between them. So on the top here we have our set input, our reset input, and then we have our Q bar and our Q output. Right, and remembering we're looking for level. So in this circuit, this actually has memory. And the way it has memory is because of this feedback. Right, it's not RAM or flash or anything like that. This circuit actually remembers its state and will hold its state. The truth table for this, S and R obviously set and reset, Q and Q bar. Q bar is simply the inversion of Q, so it's often nice and easy if you if you can work out Q, then invert it to get to Q bar. I'll fill these in binary just to make it easy. Alright, if set, now noting that these are active high, and that's always the default assumption unless you see a bar on it. These are always assumed to be active high. In this case we get a no change. Alright, so both are not active, okay, neither of them are high in this particular row, so we get no change. It's going to hold its value, whatever the previous value was. If we reset it, the output will go to 0. If we set it, the output will go to 1. And if we try and reset and reset at the same time, we enter a forbidden state. Depending on which latch you pick up and which circuit you make, it may go to all zeros or ones, or it might be completely unknown. Obviously, to fill in Q bar, we just invert whatever's in the Q column. Alright, so these typically are the three regions that we work in. You do not work in the forbidden region for obvious reasons. So to see how this works with a latch, so S, R, Q and Q bar. Alright, if I give you that and then give you a timing diagram that looks something like this, S, R, and we're just going to do Q because it's nice and simple. Alright, once again, active high, there's no bars above them, so we assume these are active high. And I always like to draw down little construction lines. Now, although these are level sensitive, I'm actually drawing my construction lines at the edge, because at that edge I assume it has gone high. Right? The level is now high, and that's the convention. So Q starting low, okay, also a convention. First set, it goes high, and at the end of the set pulse, it stays high. So at this point it remembers its state. That's that memory aspect that we see in here. Alright? Versus if it was just a normal gate, obviously its condition would change. So it remembers its state until it gets reset. It remembers its reset until it gets set. And it will continue on in that fashion until next reset. Alright? So in all of these situations, alright, we can see that this device has memory. It's actually known as an SR latch, obviously because it has set and reset inputs, set being equal to 1, reset being equal to 0. And it's a good idea for you guys to practice these sorts of timing diagrams. Draw them amongst each other and test each other on how they work. When we get to flip-flops, they are actually incredibly similar. So flip-flops, and there's quite a large number of flip-flops. First one we're going to look at is the D flip-flop. Now, as with virtually all flip-flops, it has a clock input, as well as one or more inputs and one or more outputs. The way we can tell it's a clock is because of this triangle here. If you see a bubble on it like that, then you know it's a falling edge. If there's no bubble, then it's a rising edge. In this case, rising. Now you don't need to remember how these circuits are drawn, but basically, just quickly show you how they are. So a couple of NOR gates, as we saw before, feedback between them. We're also going to add in a gated circuit and NOT gate. A little bit complicated here. So there is our D input, there's our Q and Q bar. Oh, I've got my bubbles in the wrong place there. Bubble, 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 bubble. Not reset, not set. And we have a little box here for our clock input. And this little box is the edge detector. This part here is what's known as a gate circuit. Controls whether or not the sets and resets can actually affect the change in it. And then a little edge detector here basically takes this being level sensitive and makes it edge sensitive. Alright, so that's what that little edge detector there is doing. So it's going from that to pulse. This flip-flop here is known as a D flip-flop. Okay, D for data, but D flip-flop because that's its input. And a D flip-flop works in a very similar way as what we've seen before. So make it a little smaller. Say that's our data input. Assume this is a very symmetrical clock signal. Alright, here's our output. So D, clock, and our output Q. Okay, I'm going to draw my construction lines. I'm also going to draw arrows, remembering that this one was rising edge triggered because we didn't have a bubble at this point here. So at every edge something could happen. So depending on what D is, when clock changes, that's when you'll see a change in the output of this, or you may see a change in the output of this flip-flop. So the first one goes high as per D, then the next edge goes low, stays low because we say we're just before that one there. Okay, stays low again, stays low, goes high, stays low, stays low. Alright, so you can see that even when it changes, for example in this point here, when the data input changes, even though the clock is high, it doesn't make a difference. Alright, it's only what is read on the edge of the clock at this point here. Alright, so difference, and that's very fundamental to being edge triggered. If it was level sensitive, then because any time the clock is high, then then the output could change as well. But in this case, we're only interested in what happens at that particular edge. Alright, So quick summary, sequential logic circuits have outputs that are both functions of their present inputs and the previous inputs and or outputs, as we see here. Okay, so the inputs and outputs, and then previous ones are fed back via some sort of memory element. And you may have a clock as well, okay, depending on whether it's a flip-flop or a latch. I've divided up the two where they're basically the same, except a latch has level sensitive inputs and a flip-flop has edge sensitive. Right, and flip-flops normally have clocks, whereas latches normally don't. It's not exclusive, but that's a normal way that they're used. Latches, as we've seen, set and reset for an SR latch. We have this forbidden state, and we can see that it actually remembers its state. Even after the set input goes low again, it remembers where it was. This is 0, 0, which is the no change row. Right, same as we see 0, 0, 0, 0, 0, 0. Versus a flip-flop is similar circuit, except it has a edge detector, and it's got this little gate circuit in there as well. And the idea being that now it is edge triggered, so we can synchronize everything to a clock signal, and that's quite useful for digital circuits.